All right, so this is, I mean, the final is going to be, I think it's only like 12 problems long, but most of them come from some of your old exams that you've already done, or they're similar to ones you've done. So there shouldn't be much of a surprise, except for the stuff that's chapters 10, 11, 12. So we'll definitely go over some of the 10, 11, 12 content, review some of those things. I have an example here of another hypothesis test. So you're going to have obviously a couple hypothesis tests to do. Again, the things you want to ask yourself are, is it means or proportions? Is it one or two sample, or is it deviations? So really it's going to be one of those types of problems. This one is the average on a test score. So it's talking about means. So that's why the null hypothesis here is means equals 160. A few people struggle with the notation, and if you look in your formula sheet, I give you the notation on your formula sheet. It says like mu equals mu1 or mu naught, something to let you know that that's the symbol you would use when you're analyzing population means. And then the question is, do these applicants have higher than average test scores? So they went out, these 25 people got an average of 183. So the question is 183 statistically significantly higher than 160? Then here's the t-score calculation. Get a huge t-score of 9.58. So the probability of getting this amount of difference by random chance is pretty much impossible. So that's why the probability or the p-value is essentially 0, and that's less than our alpha. So we reject the null. And some people forget this step. Explain what that means in context. So there is significant evidence to proportion the population mean test score is greater than 160. So that's like this group of folks is better than normal. And then the confidence interval it's always your sample mean, which is 183 plus or minus your t multiplier. It comes right from your t table, or you can use StatCrunch to get that. Since there was 25 in your sample, you'd use 24 degrees of freedom. And if you look at row 24, if you don't have it that accurate, you can go to row 20 or whatever. I'm not going to get too picky about this number. And then you can get your 95% confidence interval. Again, you can do these on StatCrunch as well. My encouragement to you is to even write down this formula and this formula, even without the numbers in them, just in case you hit the wrong button or pick the wrong test. For instance, on StatCrunch, I can still give you partial credit. So if these are the wrong numbers, I can still give this person 2 out of 3 points for having the right process in there. So for fun, how about we talk about interpreting the confidence interval and type 1 and type 2 errors. So would anybody want to give that a shot? How would we interpret this confidence interval? And if you want to turn your mic on, or if you want to chat it in, how would you interpret this confidence interval? I wasn't expecting to do anything. I totally get it. So what? Yes, there you go, Alexis. We are 95% confident the mean test score is between 170. Yeah, excellent. That's it. And that kind of backs up what we found here. 160 is not even close to that, is it? So we have some evidence that the actual average is much higher for this group. Very good, thank you. Now, does anybody want to try type 1 error? What would be the type 1 error for this scenario? It's a potential type 1 error. I hear a microphone.
The type 1 error would be rejecting the null hypothesis when it's true.
Very cool. And so what does that look like in this context? We reject the null and say the average is greater than 160, but what?
The average is actually 160.
Yeah, we're still good, yeah. So we incorrectly rejected, right? And how do we know when we've made a type 1 error? Well, we don't, right? Or else we wouldn't do it. That's the thing with statistics, is you can make errors and be unaware of it. Now, this may come up later when further analysis, when you get conflicting results, when things are retested and repeated, you start getting a better idea. I just had a very good conversation. There's this guy in our church who's a virologist at Drake University. This actually happened. They were digging through some old data from like even 10, 15 years ago. Well, they did a test recently, found a result that they were not expecting, noticed they may have missed something, and then they looked back at their data from 10, 15 years prior and also noticed the same trend, but they didn't see it. They weren't looking for the right thing, or was it lurking variable? And it really surprised them. It was a good case study in that sometimes it takes a long time to even see wrong things in data sets. And that's why they do lots of testing and repeat testing and more different populations and different ways of testing it. So he's actually working on, he is a PhD in working on vaccines for flu vaccines and actually coronavirus type vaccines. He's been working on that for a long time, way before the pandemic. So he's a great expert to talk to about that stuff. I watched his webinars on it. It's very intriguing. It's like even the DNA structure of COVID is the same as the flu vaccine, so it has a lot of the same characteristics of transmission and replication and mutation and which drugs it responds to and things like that. So anyway, just thought I'd throw that in. And so what would be a type 2 error? The type 1 errors, we reject the null and say it's greater than 160, but it really isn't. Type 2 error would be what?
That we accept the null, but it's actually false.
Close. We so with hypothesis testing, we either reject or we fail to reject. We never accept. So we would say we failed to reject the null hypothesis and say, oh yeah, it is 160, but it really isn't. It's really something different, but we didn't catch it. So it's either, but my Yoda-ism for this is, remember in Yoda, in Star Wars, when Luke's trying to lift the his spaceship out of the mud in the swamp, he goes, I tried, and Yoda goes, we do or we do not. There is no try. So in statistics, our equivalent is we reject or we fail to reject. There is no accept. So it's kind of weird, but it helps us, because remember what we're doing with hypothesis testing is saying, you know what, here's what we think's going on. Do we have any evidence to refute that? That's all we can really say. It's not satisfying sometimes, but the strength of evidence, the type of test, all these things lead to that. But it's a little messy and not as definitive as we'd like. But we've got some. I've been looking at people's projects, and people are really good job. Even if they're making some errors with certain things, but I'm just saying that conceptually people are getting it. I think they're trying to attack something that's kind of cool. So I encourage you to look at some of the people's video posts about their projects. There are some good ones. All right, so let's move on. So we kind of beat that one to death, but so really you're going to have a question that's with either means or proportions or two means or two proportion, something like this. And you may also have type 1 and type 2 errors, interpret the confidence interval type stuff. Make sure when you interpret your result, make sure you name the context. Like here, it's the mean is greater than 160. Say, refer to that. And there's a good one. So I've given number 2 here is a linear regression and a scatter plot. I even give you the regression equation. So this would be like chapter 10 item. So chapter 10, I may give you a scatter plot and say, you draw a line of best fit through it. Just give me an idea what you think it would be. And then I might ask you, like, do you think this is a positive or negative associationship? And do you think it's strong, weak, or no relationship? So on this one, how would you all describe this one? Just kind of looking at this. This is a relation of reading speed with typing speed. It is definitely positive. Very good. What else? Do you think it's strong, weak, moderate? No. I mean, what do you think? Yeah, it's pretty weak. Why? Why do you think it's weak? There's a few outliers. So when data points are off that line, it doesn't build confidence, does it? Now, if all those data points were right on the line, we'd be like, wow, this is really strong relationship, really strong correlation. As this variable increases, the other one increases. But what we're seeing here is a lot of spread out, right? It's not a very strong model. In case we look at the R value is 0.35, and I know you've done some homework on those. And what's the highest R value you can have on a positive correlation? If anybody remember that from your homework, what's the yeah, 1. And then if it's a negative correlation, the strongest would be -1. That'd be a downward trend. And the closer the number is around 0, the less it's kind of like the less sloped, or the less change we see. So this R value is 0.35, so it's a weak positive correlation. And then I asked you to do a residual plot. So a residual plot is really saying if I just do this line, how does the data fit around it? So notice this one right here. This first one is above the line, above, below, below, right? So it's just you make a horizontal line and then you plot the data points above and below based on how are they in respect to the line. It helps you not worry about the slope. It lets you look at, does the data look like it's got a pattern, or does it look like it's random? What do you think here? Do you think we have a pattern here in our scatter plot or in our residual plot, or does it look pretty random? What do you think? I don't think it's very obvious. And notice I've got the answer right here. It says there may be a pattern. Notice we go above the line, below the line, then above the line. And if I was going to pick the next one, it may be above the line, right? What we'd like to do is see a really random pattern here, and then that would be probably a good fit. But if we're seeing a trend, it may not even be a linear trend that we're looking at. So just be, kind of looking at that, but be able to make a residual plot, look at it, look for randomness would be ideal. So is this a good fit? No. We've got a low R value. There may be a pattern, so this isn't probably a great fit. But if you did use it, what prediction would you make for a typing speed of 65? Well, it gives you the equation right here. You just put 65 in for X and solve it, and there you go. Now, the one thing that's not asked on this that I would add on is it asks what is R squared. So R squared is 0.3519, squared is 0.12. And does anybody know what that 0.12 would represent from that homework? What would the 0.12 represent? R squared. Maybe remember that in your homework? The R squared value is the percent of variation that's explained by that variable. So what that would be saying is a percent of variation in reading speed, only 12% of it is explained by the speed that someone can type. Not a lot of it, right? So your typing speed does not necessarily, dictate or explain reading speed, and probably vice versa. So it's a weak correlation here. How's that? So the percent of variation that is explained, that is the R squared. And I think I'm going to move on. Any questions on those first two, I guess? Hypothesis test, confidence interval, linear regression, scatter plot, or a residual plot, taking predicted values. If a dot is above the line, we call it a positive residual. If it's below the line, it's a negative residual. So for instance, I've got a really old car. It's sitting out in the driveway. It's a 2001 Town & Country minivan. All right. It has been depreciating a lot over the last 19 years. Now it's probably not a linear depreciation, although the last few years it's probably staying pretty linear. Usually that's an exponential decay, which means it drops a lot initially and then it levels off. So the older the car, the less it depreciates each year, percentage-wise. So let's just say, what are some reasons why a car might depreciate? You can give me some variables. Why would a car depreciate? As in, depreciate as in is worth less and less. Yep, wear and tear, very good. What else? Yep, how old is it, right? That's definitely will dictate how much it's worth. What else? Yeah, if you got any accidents or it's got a salvage title on it. There's one other big one hasn't been mentioned yet. But what lowers the value of a car? Newer models, that is definitely, if a new body. Yeah, you drive it off the sales lot. Yeah, there you go, Catherine, got it. Mileage. So the more miles you drive, right? So you can make scatter plots that shows the value of the car versus all these variables, right? As mileage increases, the value decreases. As the years get older, it decreases. So if I'm saying the percent of variation that's explained, that means some of these variables are more important than others, right? Is the age more important than the mileage, or is it more important that there's been an accident, or there's been a new model that comes out that makes the old one look like old? There's a whole bunch of variables that will dictate those. So you're just would I want so let's say my 2001 minivan, according to Kelley Blue Book, is worth $900. Would I want my van to have a positive or negative residual on that prediction? Yeah, I would love for Jeff. That means it'd be worth more than what's expected, right? And if it's worth less than what's expected, it has a negative residual based on that prediction. So I always like to use my 2001 minivan as an example. Oh, no, you will not have to make your own regression. Nope, it'll just be given to you. Or it'll just be a scatter plot for you to analyze. All right, this next one is a goodness of fit. There will be one very similar to this on your final. This is from chapter 11. This is a uniform model, which means we would expect the frequency to be the same each of the times. When you roll a die, we would expect there would be the same frequency of each number to come up. Die is rolled 48 times. It asks, what's the expected value? What would you expect it to come up? So 48 divided by 6 would be 8. So there should be 8 occurrences. Now, obviously, this doesn't happen, right? But there's some variability. The question is the variability explained by randomness or not? This is what stats helps us figure it out. So again, here's the chi-squared formula, and I show the calculation here. So like 13 minus 8, so that happened 4 or 5 more times than it's supposed to. So 5 squared is 25. and then you divide that by the expected, which is 8. And you do this for each one of them, you get a chi-squared statistic of 22.25. So you could actually put that in your chi-squared calculator in StatCrunch. There would be 5 degrees of freedom, or you could look at your chi-squared table and notice if you look in row 5, 22.25 is a very rare event. That's a lot of variability. This tells us we should reject the null, and the null hypothesis for this one would be that it's a fair die. They should be equally distributed. The alternative is that one or more of the numbers does not fit. It means it'd be like a loaded die or not a fair die. So we'd reject the null and say this is not a fair die. This did not pass the test, and Vegas would not use this die. So your null hypothesis is that it's all good, that it fits the model. Your alternative is that it does not fit the model. Questions on that one? All right, and then this last one here, it essentially gives you a data printout. The situation here, it says, yeah, this is not a very good example, which is why I probably don't use it anymore. It doesn't give you any context, which is kind of ridiculous. So let's say I did give you a context. Let's say we're looking at, let's see here. Let's say we're looking at the houses in a neighborhood, the average house prices. And the null hypothesis would be that they all come from like kind of all the same average price, right? From each of the neighborhoods. So like I live in Beaverbrook here in Grimes, the old Beaverbrook 1. It's like Beaverbrook, I don't know, a dozen now. There's a bunch of nicer, newer homes to the west, right? But we could say, okay, what's the average price for Beaverbrook 1, Beaverbrook 2, Beaverbrook 3? We could actually analyze all of these and find if there's a significant difference in any of the means. So let's say that's what we're doing. Our null hypothesis is that mu1 equals mu2 equals mu3 equals all those population means are the same. All those neighborhoods have the same average home price. The alternative hypothesis is there's at least one neighborhood that's different. Well, if I gave you that printout here, just by looking at this printout, what would you think? This actually would be one of, I think, 4 different means. But if your null hypothesis is that all the means are the same, the alternative is there's at least one different. What decision do you think we could make here just by looking at this printout? So DF is degrees of freedom, sum of squares, mean squares, your F distribution, which you did do some F distribution problems in this class, but that's not really that important here. What's the one thing you need to look for? Yeah, p-value. Yep. So p-value is 0.011, and that's usually, and that's when we had a 0.05 significance level. But in general, that means the probability that we'd get this much variability by random chance is about a 1% chance. So we would reject the null because it's p is, and we say there is significant evidence that there is a difference in one or more of the means. They're not all the same. Something that affects. So this one's not a great problem, but at least gives you an idea of how you can. It's kind of like chapter 12 stuff, right? Analysis of variance. All right. Questions on this supplement to the final? There are some questions on just basic, like what's a sample? What's a population? What's a good sampling technique? Random. Why? Because it reduces bias. It makes it more representative. Just some general knowledge stuff that you got from your previous exams. There will be some stuff on binomial probability, and there will be some stuff on general probability, very similar to your second exam. So definitely take a look at those. Then there's going to be some z-score problems, like area left, area right, area between. which are very similar to your chapter 6 questions and actually chapter 3 questions that we had from the first exam. Pull up another example here. Hold on. Let's see here. Let's see if this has got any problems on it. Here's another supplement. I think this one can also be found on Blackboard. I'll see if there's anything on here that looks worthwhile to talk about. Here's another example of, oh, this is exactly the same as that one. See if there's anything different on this next page. Yep, that's similar. There's a residual plot. Yeah, it's just, this one's pretty much the same thing. Oh, here's a good one. This, so Brandon, this will be good for you. Oh, no, it won't. Kind of. Kind of. This is for test for independence from chapter 11, but we could actually do this as just a basic probability one. Let me pull up this off Blackboard. Hold on. Here we go. Oh, that's a pretty good example. Let's see if I get this other one. Yeah, that'll work. All right. Do you all see that one now? I want to do that. I want to share screen. Okay. So here's an example from 2013. Very similar type problems. It actually has you make a scatter plot and a residual plot based off the raw data, which I don't think I asked you to do that anymore. This one has a strong positive. This one has a very strong R value. This is a good one to practice finding R squared and all that good stuff. So that's not that exciting. There's definitely a pattern in the scatter plot, so it's probably not a good fit. This is the one. Right here. There we go. So this one has, we can do, don't worry too much about the chi-squared stuff on here, but look at using this as a basic probability one. So if I ask, go ahead and chat in your answers, everybody, what you think this might be. So we've got health insurance, no health insurance, men and women. So if I randomly pick somebody, what's the probability they would have health insurance? Go ahead and type in that. You can just type in the fraction if you want. If I randomly pick somebody, what's the probability that they have health insurance? So Brandon, this is for you too. Just 70 out of 110. Very good. Okay. So 70 people have health insurance out of 110. Okay. What would be the probability that that a woman has health insurance? If I randomly pick somebody, what's the probability that it's a woman and they have health insurance? How about that? Woman and they have health insurance. So it'd be what, 20 out of 110. Yeah. Now, this is a little different. This is when we do the given, okay? What's the probability that the person has health insurance given it's a man? This is a little tricky. I'm going to say that again. What's the probability that the person has health insurance given it's a man? If you get this, that'd be amazing. Wow, good job. 50 out of 80. So if I say probability that they have health insurance given it's a man, that means they have to have both insurance and man. How many have that? 50. If I say given that it's a man, that's the only group we look at now. So it's 50 out of 80. Excellent. All right, let's try another one. What's the probability that they're a woman given they have no health insurance? A woman given they have no health insurance. Ten out of 40. Good. So if I say they have no health insurance given they're a woman, that means how many are both no health insurance and a woman? 10. Given they have health insurance, the second thing. That's the only group I'm looking at. 10 out of 40. It's tricky. How about this one? What's the probability they are a woman given? No. What's the probability they have no health insurance given they're a woman? No health insurance given they're a woman. There you go. 10 out of 30. So now you just compare it that way. So the second thing, the given part, becomes the new population you're comparing it to, the new subgroup. That's a little tricky. So just looking at this, does health insurance seem to be independent of being a man or a woman? How would you figure that out? Essentially, are these independent or are they dependent variables? Do we seem to see like it doesn't matter if somebody has health insurance if they're male or female, or does it matter? How could we even attack that question? Obviously, you can look down here and do a chi-square just attack of it, but just look at it from a straight probability standpoint. Don't even look at down here. Just look up here. How many? How many men have it? 50 out of 8. How many women? 20 out of 30. Are those proportions the same? 50 out of 80, the same thing as 20 out of 30. That's 60%. What's that? 60. That's going to be what, 0.625? Is that what it is? Oh, that's interesting. Yeah, 0.625. So that's 0.625 and that's 0.666. So they're close. If there's any difference, we could start to say, yeah, there might be something going on here, which is why we actually in chapter 11 do goodness of fit test here, or test for independence here. And if you, I don't ask this on your final, but you can see how they on the expected value for each. You did some of these in your homework and did all that calculation, and the chi-squared is very small, and there's not enough evidence to say there's something going on here. It does not depend. Not enough strong enough evidence to say that there's a difference statistically between the two, even though there's a slight difference. That's how we would do that one. But you could use this as a basic probability example for chapters 4 and 5, and you can use it on your final. And then Brandon, that'll help you on that other test too. Going through that idea. And here's a good one. This last one. I used to ask this question all the time. Farmers concerned with the effect of snowfall levels on their crops. Amazing, it snowed today. Can't believe it snowed that much today. Farmers concerned with the effect of snowfall levels on their crops found that there wasn't evidence of a decrease in crop growth. There was not evidence of a decrease. That screams to me they did not have enough evidence to reject the null hypothesis, right? So their test statistic and their result was somewhere in this area over here. The basis conclusion alpha level of 0.1. That means the only way they said that there would be statistically significant evidence is if they got a test statistic that was down in here below this 0.1 threshold. So it says, would they have made the same decision at 0.05 and at 0.01? So obviously, if they didn't reject at the 0.1 level, they would not reject at the 0.05, and they would definitely not reject the 0.01. So they'd make exactly the same decision, not a statistically significant decrease. There's a whole bunch of examples in some of your old exams like that. Just the conceptual understanding of significance. When do we start saying that's a rare thing or not? I think that's it for that one. I have been grading some of the finals. Some people have done them already. I'm pretty good. I am trying to see if there's anything. I would strongly encourage, just go through your old exams from this semester, and you should be fine. There shouldn't be, and then I've kind of gone over the chapters 10, 11, 12 questions that you have not seen. That's what I've been focusing on, going over some of those. But I don't really have any more examples, I think, that you need to see. So if you go through your previous exams this semester, and you've gone through these chapters 10, 11, 12 examples, you should be ready to go. Yeah. Yep. I don't think there's anything weird. And I would say just, when you're making your final conclusions, make sure you use context. Make sure you say it in relative terms to the context, like that one, like if it has to do with the test score, or if it has to do with, what was this? Oh, no, that's not a hypothesis. Or like we just went, house values. If you're going to reject them, I'll try to make it contextual. Starting here. All right, so I've gone over some of that stuff, and that is available on Blackboard as well if you want to look back on it. I even think I have a solutions video going over one of them as well. As far as reviewing for the final, specifically chapters 10 through 12, I think I've shown you pretty much what you could expect on there. The rest of it is going to be from your old exam. So I don't know if is there something from one of the previous exams that anybody wants to go over? Were you able to watch those solutions videos and kind of find your errors on those? So that might be worth some time. If you have not done that so far, that may be worth your time just to go back, review the exams you took for the 3 exams you've already taken. I'm going to stop the recording.